States of matter are nothing new to you. So you've done these in first year, you've probably done them in chemistry a few times. But just to remind you, because these are important when we go on to talk a little bit more about gases in this topic. So solids are in a regular shape, they're held closely together. The particles can vibrate, but they can't really move any further than that. So all they do is just vibrate in place. Liquids, they're still quite close together, but they're not held in a regular shape, and they can move around on top of each other. So they can move around a lot more, but there's still quite a lot of them in a small space. Page 18. And gases, well, the photocopying is not great on this. I hope it's better on your booklet. But gases, the particles are much further apart, and they can move around a lot more, and they fill up the space that is available to them. Okay, and they move randomly and collide with elastic collisions. And it's those collisions that are really important when we go on and talk a little bit more about gases, because they do define everything that happens in a gas. Is your photocopying better than that? Do you have the last bit? Okay. So just a little diagram to show that solids to liquids to gases, and hopefully you've got the gases on there. Solids, molecules held in fixed position but vibrating. Liquids, molecules packed close together in a random fashion, and they're free to move, but they're still packed together. And gases, the molecules are widely separated, and they move at great speed. And those are the changing states in between them, which we are familiar with now, which require energy. So melting, we use melting rather than liquefying, and freezing, we prefer freezing to solidifying. And then from liquid to gas, we have boiling or evaporating, and from gas to liquid, we have condensing or liquefying. And sublimation is that top one. That's when it sort of bypasses the middle step. Okay, and those of you that do chemistry will be aware of all that already. And those of you that don't do chemistry, you definitely have done this earlier on in your physics career. Yes, Jamie? Same. Yeah. Just like, well, yeah. Okay. So, kinetic theory. So, kinetic theory is the theory of all of those particles sort of moving around, and the way that they move around and the way that they're organized defines how a material acts. And the evidence for kinetic theory is Brownian motion. So I've got a nice little video that I shot in my first years that I will show you again. But Brownian motion, Brown, the scientist Brown, what he did was he put smoke particles underneath the microscope, and he observed them. And what he saw was the small smoke particles sort of moved around, danced around randomly. And what he proposed was that what they were doing is they were colliding with randomly colliding with air particles that you couldn't see. So all you could see was what the small particles was reacting to, but you couldn't see the air particles. So let's put this video on. It's only a short one.
Gases behave gives us clues about how their particles are arranged. In solids, the particles are in a fixed framework. They're held close together and vibrate. In liquids, the particles are still in contact, but this time they're free to move around. The particles in a gas are far apart. They move quickly and randomly in any direction. But how do we know the particles in a gas behave this way? Some of the evidence comes from looking at how smoke appears under a microscope. Smoke from a straw is injected into a small container. A lid keeps it in place, and a bright light allows it to be viewed under a microscope. It looks like tiny jiggling points of light. When a straw burns, the smoke produced is mostly bits of carbon which haven't combusted. Under a microscope, they catch the light and appear to glimmer. But why do they randomly dance around? The movement of the smoke is caused by collisions with invisible air particles. As the air particles move about, they knock the smoke first this way, then that. Particles in a gas move randomly and quickly.
That's the evidence. So, back to our notes. So the specks of smoke are seen to be continually moving around. This is because the tiny, fast-moving, invisible air particles which surround the specks of smoke are continually colliding with them. And due to the random motion of the particles of a gas, the particles of any gas will eventually spread themselves out to fill any space available to them. If a dish of perfume is left in a room, the molecules of perfume evaporate and spread out throughout the room so that the perfume can eventually be smelled everywhere in the room. And this process is known as diffusion. Okay, so, sorry? Yeah, same for any kind of gas spray. Yeah. Right, so we need to keep, girls back, we need to keep those particles in mind when we go on and we talk about more in this booklet, because everything is related to how those particles move and how they're squished up or spread out or how many collisions they have. Because we're going to first of all talk about pressure. Okay. So you've probably all heard of pressure before, and you probably sort of know what it is. You know that you can apply pressure, and it's all to do with the force that you apply. Most people don't realise it's actually to do with the area that force is applied on as well. Because you probably can tell straight away that if you apply a bigger force, you're applying a bigger pressure. That's sort of, yeah, makes sense. But the pressure is about area as well. So pressure on a surface is defined as force acting per square meter at right angles to the surface. So basically what it's saying is the smaller area, the bigger the pressure, or the bigger area, the smaller the pressure. So pressure is measured in pascals. It's named after a scientist, P little a. And force is obviously measured in newtons, thank you. And area needs to be in meters squared. Okay. So you'd be absolutely right to say that the unit of pressure could also be newtons per meter squared, because it's newtons per meter squared. But it's been named Pascal after one of the scientists who discovered it. So the unit of measurement of pressure is the Pascal, capital PA, and it's equivalent to 1 Newton per square meter. So 1 PA equals 1 nm to the minus 2. Standard atmospheric pressure is 1.013 times 10 to the 5 pascals. We usually just simplify it to 1 times 10 to the 5 pascals. So that's 1 with 5 zeros at the end of it. So atmospheric pressure is actually pretty huge. But we don't notice it because we have equal pressure pushing back out again. So we have that much pressure, 1 times 10 to the 5 pascals, pushing in on us at all times, but our body's also got pressure pushing out. Okay, if we didn't, then we would implode. If we had too much pressure inside, we would explode. Okay, so atmospheric pressure is affected by weather conditions, altitude, and temperature. And just thinking back to that pressure equals force over area equation, so what it means is the bigger the area, the smaller the pressure. So pressure is inversely proportional to area. And the way to think about that is you can get things like snowshoes, which increase the area that you're standing on, which therefore decreases the pressure. So basically you don't fall into this, you don't dig down into the snow. Similarly, stiletto heels, or very, very thin heels, they have a very small area. So if you stand on somebody's foot in stiletto heels, it hurts a lot more than if you stand on someone's foot, just a normal trainer. Okay, because the stiletto heels have such a small area. So it's all to do with area. So it's also the pressure is to do with the area as well as the force. So let's do some examples. What is the pressure, girls, exerted by a mass of 6 kilograms placed on a horizontal surface of area 0.2 meters squared? So we know that we can work out pressure because it's force over area. We've been given the area, but we haven't been given the force, we've just been given the mass. Now, what is the force of something's mass? What's the special name for something? The force downwards towards the centre of the earth? You weight, yes. So if you've got a mass, you can work out its force downwards by working out its weight. Okay? So the force equals a weight, which, what's the equation for weight? Yes. So in this case, it's 6 times 9.8, which is, because my pen didn't work, 9.8. There you go. Which is 58.8 newtons. Yep, so that means that's the force that you put into your equation. So pressure equals force, which is 58.8, divided by the area. It's in meters squared, so that's fine. Which comes to 294 pascals. That's snowshoes. So they're like old-fashioned snowshoes. So you could tie them. They do look like tennis rackets. And they kind of work. You could tie tennis rackets to your feet in the snow, and they would work in the same way. You're increasing the area that you're walking on. It does have holes in it, but it's still increasing. It's still a bigger area. If you put your feet in the middle of there, it's still a big area. Okay, example 2 is a tricky one because it's giving you the wrong units. So what is the pressure exerted by a mass of 60 kilograms placed on a horizontal surface area of 2 centimeters squared? Okay, so again we'll be using pressure equals force over area. We've not been given the force, so we need to work that out. And we've been given the area in centimeters squared rather than meters squared. So first of all, let's find out what the weight is. So our force is the weight, which is mg. So 60 times 9.8, which is 588. Now, to go from centimeters squared to meters squared is not the same as going from centimeters to meters. Okay, now you won't need to do this in National 5, but it's just an extra information for those of you that like that kind of thing. So, to go from centimeters squared to meters squared, you have to times by 10 to the minus 4. So whereas normally it would be times 10 to the minus 2, it's times 10 to the minus 4. And that, in case you're interested, is because 1 centimeter squared is 1 centimeter by 1 centimeter, isn't it? You don't have to write this down, this is just for information. So 1 centimeter is 0.01 meters. So 1 centimeter squared is 0.01 times 0.01 meters, which is 1 times 10 to the minus 4 meter. So that's basically where that comes from. Okay. Don't worry if you're like, what are you talking about? In terms of National 5, but that's just where it comes from. So, pressure equals force over area. So the force is 588. And the area is 2 centimeters squared. So 2 times 10 to the minus 4 meters squared. And that pressure comes to 294,000 pascals. So 2,940,000 pascals. So just for information as well, if you wanted to change from a millimeter squared to a meter squared, you would end up having to times by 10 to the minus 6 rather than times 10 to the minus 3. Okay. It would be times 10 to the 6 rather than times 10 to the 3. Right, okay. Sorry, leave that for a little bit longer. We are going to do an experiment next. This sometimes works, sometimes doesn't. So, but I know that you're dying to do experiments because you don't get to do many anymore. Sorry? Who set it up? Me. Okay. Right. So, you will see in a second on your desk, you have got 3 things. Okay. So, you have got what we call a bourdon gauge, a syringe, and a Newton meter. Okay. So, bourdon gauges you haven't seen before. It's something new, and they measure pressure. Okay, you'll be able to look at them when you're doing the experiment as well. So, bourdon gauge has a curved metal tube connected by a series of levers to a pointer on a scale. Okay, so the scale, you can see a picture of it there. It's an analog scale. Well, the ones we've got anyway are analog scales, so you have to read from a scale. If the pressure inside the tube is increased, the tube straightens out, moving the pointer around the scale. Provided a fixed value of pressure is known so that it can be used as a reference value, then a bourdon gauge can be calibrated using the following procedure, which we're going to do now. The gauge can be attached to a syringe and then a force applied to the piston of the syringe. The resulting change in pressure can be calculated by dividing the applied force by the area cross-section of the syringe. So pressure equals force over area. Right, so what you guys are going to do is, this is it's not a difficult experiment, but there's a lot of things going on at the same time. So you all need to be sort of watching various scales because you have to do it. You have to record a few things at a time. So what you're going to do is you're going to get your equipment, and you've got the gauge attached by a little tube to a syringe, and then your syringe should have a little loop on the end of it, so you can pull it with a Newton valve. You need to make sure somebody's holding the syringe at all times, otherwise the tube will just pop off and it won't work. So somebody needs to pull the syringe and record the force that they are applying on the Newton meter. While they're doing that, somebody else needs to record the change in pressure on the bourdon meter. You see, it has to be recorded at exactly the same time, otherwise it doesn't work. So somebody needs to watch this, somebody needs to watch the Newton meter, maybe somebody needs to hold this as well. Or you can do the same person holding the syringe and the Newton meter. So, what you're going to write down is the initial pressure indicated on the gauge. You can just write that down as it is when you first see it. Okay? So mine, I think, is 1 times 10 to the 5. You'll see when, let me show you the gauge. Whoa. I don't know what's happened there. Let's try it again. Try opening that again. Right, anyway, you'll see on your gauge that it has right at the bottom times 10 to the 5 pascals. That means that anything between is times 10 to the 5. Okay? So if it's pointing at 1, as mine is, it's actually 1 times 10 to the 5 pascals. So my initial, yours should be around about 1, it might be slightly different, but my initial one is 1 times 10 to the 5 pascals. Okay? The final pressure is the pressure it gets to when the person's pulling the Newton balance. Okay, so that's what you need to write down. You don't need to pull it, so don't break anything, basically. Yeah. No. Then you can work out the change in pressure by taking one from the other. Okay. The force on the syringe piston is what you're reading from your Newton meter. The diameter of the syringe piston, you use a ruler, and you're going to measure this diameter here in meters. So this is the diameter across the sides. Okay? And the area is just area of a circle, so pi r squared, so pi diameter divided by 2 times squared. Okay? And then your change in pressure is your force over area. So the things that you're recording when you're actually doing the experiment is this and this. The rest of it can be done at any time, okay, with calculators, with ruler. Okay, so those are the 2 values that you need to record when you're doing the experiment. Okay, and hopefully your change in pressure here should be the same as your change in pressure here. I'll do the experiment at the front as well, and I'll get a sample set of results just in case anything goes wrong. But remember, you need to hold on to that syringe, otherwise it won't work. It'll pop off and it won't work. And you need to watch the gauge and the Newton meter, and you need to go right now. What is the value now? Okay? Any questions? Right, off you go.